My name is Jesse Burns. I'm a principal partner with Information Security Partners. We're a security consulting company, and I'm based out of San Francisco. I'm going to talk today about fuzzing selected Win32 interprocess communication mechanisms. I'm going to focus on just a few of them because there's a huge number. And what's a Win32 IPC mechanism is one of the things I'll cover, but you know, I'm looking more at things that are specific to Windows programming, not Berkeley sockets type stuff. So I'll be starting with a little bit of a background of fuzzing and some information about Windows IPC. Then I'll talk about mechanisms for identifying the communication channels to test. Turns out that determining the attack surface of applications isn't always obvious. And I'll cover a couple of tools, give some demonstrations, and then I'll jump into a mechanism that requires a little coding. That's doing it with code hooking and using that for finding name pipes, which kind of leads into using that for testing name pipes and for testing generally any kind of IPC mechanism, with name pipes as sort of the example. And then I'll jump into another mechanism, which is shared sections, just kind of briefly. And there's going to be demos throughout. And I should say that we've got sample code. There's a zip file on this CD, which is floating around. And there's code on our website, which I'll give you an URL for in a little while. The code has different components in different languages. All of it compiles with Visual Studio 2005 Express Edition, which is available free of charge. And all of it's available under pretty liberal licenses. Our code's under GPL. Some of the dependencies that we use, like Matt Conover's libraries, are available under a BSD license. And these are our public fuzzing tools. They just kind of give you all the examples that we're doing here today, and I think a few other things. So what's fuzzing? A little introduction. Fuzzing is when you take some program that you have and you have data that it accepts. Maybe it accepts usernames, and it's expecting a string, maybe a 1 to 10 character ASCII string. And instead of giving it a 1 to 10 character ASCII string, you give it the worst possible thing you can think of. You give it really big strings, you give it null strings, you give it multi-byte data, you give it Unicode, every bad character you can think of. Just, you know, throw it all at it and see what it does. If you have input, you want to know if providing bad input can cause your application some problem. Generally, your program is going to have two kinds of input. It's going to have input that it trusts and input that it doesn't trust. The real difference here is difference between the two is whether or not the person providing it or the entity providing it has an identity relationship with the service process. And so if it runs as the same account, well, you don't have to worry about it. If it runs as some other user, even if the other user is also a low rights user, you do, because you're going to have access to things that it doesn't have access to. So software binaries themselves are actually, you could think of as trusted input. So that means they have to be ACLed correctly. Obviously, when programs have bad ACLs, attackers can overwrite the programs, and when trusted users run them, they're exposed. Scripts, libraries, all the inputs to a program from a database, if the database itself is the thing that the program protects access to, that's usually trusted. Untrusted is where it gets interesting. That's anything that comes over the network, obviously. Anything that comes from files that aren't ACLed. If you download my PowerPoint slides off the website, or this zip file filled with tools that I'm recommending you download, open up and run, maybe recompile, all that's untrusted input. And you know, you should be careful where you accept it from. So when you're doing security testing, we want to make sure that we trust all the vectors into our application for untrusted input. We want to make sure that no matter what comes in there on these untrusted channels, you can't crash the application, you can't cause buffer overflow that's exploitable, you can't make the CPU go to 100% and stay there for a half hour, you can't make it allocate all of its memory. Then you can also use do this kind of testing on trusted inputs, but that's just really robustness testing. It's not the kind of stuff that we do at ISEC. But you can actually use fuzzing for both kinds of input. And if you find some issue, great. That's nice to have, especially if you're integrating it into your QA testing. It's good to be able to get some additional benefit. So A lot of Windows IPC is based on securable objects. And securable objects are this standardized design that Microsoft has for kernel objects. So when you get one kernel object, like a socket, it's got a lot of the same attributes as a file, or as a registry key, or as a named pipe, or a section. All these objects have features that are the same, and they have things like discretionary access control and mandatory access control, that's auditing. So if an administrator knew that a certain application used name pipes, they could go in there and they could say, oh, I'd like it to audit whenever someone fails in their attempt to access this. In practice, most administrators have no idea what IPC channels are being used on the system, but it's a nice to have, and it's great for, when you think about it, in the future, HID systems, things like that, might start instrumenting these things and using those kinds of things. So one of the other things that's true about these IPC channels is that some of them are only accessible locally. So a lot of the privilege escalation risks that I'm looking at are going to be local host privilege escalation. So I've got a low rights account and I want to make it into a high rights account. I've got a low rights account and I want to take out the service that reports my bad behavior to the system administrator. Anything like that, that would be local. But there's also a remote aspect to these, especially with things like name pipes. They can be accessed from any machine on the network, and you have to be a little more careful with them. If you don't intend to have it used remotely, then you have to specifically ACL it so that it can't be used remotely. And that's not too hard to do, but requires a little bit of effort. And it's often not done. So one of the other interesting things about these Win32 IPC things is they tend to be highly compatible between versions of Windows. You can find that NT3.1, the first version of NT that was multi-user, like the first version of Windows that was multi-user, has a bunch of similar IPC mechanisms to Vista. And you know, this stuff even works between NT and 2003 server. So. So I'm going to just talk a tiny bit about what the attributes are that these securable objects share. So one of them is the discretionary access control list. The DACL is you know, the thing that you have to set right. If you have a multi-user system, which Windows is, and you're writing code for it, you absolutely have to secure it so that it's safe in a multi-user environment. You might not use your computer personally in a multi-user environment, but lots of people do. This is becoming even more important with Windows Vista, because under Vista, the default is that users run with low rights. Mandatory auditing is another feature of all securable objects. Again, rarely used, but it's certainly powerful. And owners. Owners are the little people that created the object, usually. You can end up being the owner of lots of interesting objects on your system, and you can always change the access control list, at least the discretionary one, if you're the owner of an object, which means administrators who try and lock you out of your own files by changing the ACL on them, well, they haven't done a very good job. So there's another attribute called integrity level that's new to Vista, which I'm not really going to talk about today. And then one other attribute is not universal, but occasionally occurs, is the idea of names. And names are a really important part of Windows IPC. Names like, I know you've seen files, so files have paths, right? Well, a path for a file is just a name. It's a shared object that's named. One of the nice things about naming an object is that you don't have to have an inheritance relationship with the process that created the object in order to access it. So if you have an anonymous pipe, you have to basically create a child that has access to the same handle. Well, with a name pipe, you can create a name, and then both those processes can open that pipe up. Now, names don't just apply to named pipes. They also apply to a bunch of other IPC mechanisms. And just because you can't type in dir on your command shell and see them doesn't mean they don't exist just as much. Obviously, registry keys have names, but mail slots have names. Mutexes can have names. Some objects don't have to have names. Like, it'd be pretty useless to have a file that didn't have a name, but there's nothing that says a semaphore needs to have a name. It's used for thread synchronization, and if it doesn't exist outside the process, if it's not used outside the process, there's no need to name it. And in fact, most of these objects aren't actually named, and they only really become part of the security surface of the application when they become named, unless you have untrusted children, which is a very rare condition. So, here's a big list of some of the Win32 IPC mechanisms. Hopefully some of these are things that you haven't seen before, but maybe none of them are. Events, event pairs, files, keyed events, LPCs. LPCs are an undocumented but fast IPC mechanism. Some of these, like sockets, are never named. I mean, they have the idea of maybe a port associated with them or something, but they're not named. And they don't get part of the namespace. So I'm going to just focus on a few of these. I'm not really going to, I can't talk about everything here. I'm going to talk about some of the ones that are the most common. So probably the most common Win32 specific one is the named pipe. So named pipes are kind of like sockets. They're either UDP, or sorry, message mode or stream based, which kind of looks kind of like UDP or TCP. They can be accessed locally or remotely. And the remote version is based on SMB. So just like sockets, you wouldn't expect when you open up a socket that you get any confidentiality protection on the data that you transfer over it. Well, just because you're using this thing that you found in the back of some book, this named pipe, doesn't mean you get any more confidentiality protection on it. You may, if you've got your SMB tuned up nicely, you might get some integrity protection at least. But determining that on a particular system, this configurations are just right so that it takes advantage of, Kerberos authentication and Kerberos authentication only, or NTLM v2 authentication and NTLM v2 authentication only, and not some obsolete mechanism, and that it uses signing for all of the messages. Those aren't the kind of things that are easy to determine, and there's no easy programmatic way. So you just generally assume that, like you would with a socket, this data, when it comes in over the network, is totally untrusted. It might have been intercepted, and if you want confidentiality and integrity protections, you better layer them on top. Shared sections are a named block of memory. So it's kind of like an mmap, if you've used that system call. You get a region of memory, and you can map it into as many processes as you want. So really fast, and really a great way if you need to share your structs or something that you don't want to have to come up with a fancy way to marshal. And they have no they don't have a synchronization mechanism. With a named pipe, when you stuff a message down, on the other side the read returns. Not so with a section. With a section, you just have a block of memory, and when you scribble in there, whatever you write is in there for anyone else who wants to look. And if you want to tell them, hey, you should go and look in there, you have to do it through some other channel. So because of this lack of synchronization, data validation can be really problematic, and we'll talk about that a little more later. But one of the other things that's nice about these, or not nice, but that's essential to understanding their nature, is that they're local only. You don't have shared sections across a network. There are systems that do shared memory across a network. It's inefficient, and it's inefficient relative to on a local host. So events are almost the opposite of sections, where sections just give you a message and no signaling. Events give you a signaling and no message. So when I have some event that occurs, I can wait for it. I can say, I'm going to wait on this event, and when someone pulses that event, I can say, all right, now it's the moment. It's just one bit of information, and that is that whatever the context-dependent thing that this event was associated with has happened. So you should wake up and do whatever you're going to do. One